So those kind of give us some background in terms of the physiology and the underlying haematology, but why do we assess haematological variables? Now, to a certain degree, you've probably got a gist of that already. Well, one of the things is we understand its importance in response to training. So one of the things we know is plasma volume can increase within 24 hours following exercise and actually achieve around about 10% above pre-training 1 to 4 days post. So we know that plasma volume responds to training. So if we then extend that a stage further and we think, okay, we've got to say a 2-week block of training, all blood volume expansion can be accounted for by plasma volume expansion. So we get an increase in blood volume, and we'll explain why this is the case in a moment. But actually, predominantly, the big variable that accounts for that with training is plasma volume is expanding. And the reason the plasma volume is expanding is to fundamentally facilitate a decrease in the resistance to blood flow, to allow for the erythrocytes to be delivered more effectively with less resistance to flow than was happening pre-training. In other words, we accomplish this with no significant effects on the blood pressure. If we then go to say 2 to 3 weeks of exercise, now we start to see things like erythrocyte count increasing. So it starts to expand. But it's an undetermined rate. And actually this is a really important part. It is undetermined, and it's fundamentally a function of the underlying genetics of the individual, not surprisingly, but also it's fundamentally linked to the intensity of exercise. It's linked to the recovery and the kinetics of recovery. So simply just exposing somebody to a single training session will not suddenly increase red blood cell count and expand the erythrocyte volume. But if we accumulate that training, then it's the totality of the accumulation that drives up the biological adaptation that starts to create the changes in the cellular environment. And if you go back to where we started this presentation, which was a major driving factor here is the process of erythropoiesis, there has to be a large enough shift in the cellular CO2 concentration and accumulation to stimulate the process of erythropoiesis enough to drive up the increase in red blood cell volume, to drive up the increase in hemoglobin concentration, to compensate now for that change in the cellular environment. So what we start to see is over roughly a 2 to 3 week period of training, yes, you get the increase in erythrocyte volume, but actually what starts to happen is that the hematocrit volume is re-established. So it starts to kind of compensate when we look at this as kind of a percentage of one variable to the other. So the plasma volume expansion itself is actually very, very important to understand. Well, how do we achieve plasma volume expansion? Well, it's easy. We just retain more fluid. It ends up with, in an endurance athlete, you tend to see slightly lower hematocrit concentrations, but higher red blood cell counts. The hemoglobin concentrations tend to be, in an endurance athlete, tend to be higher, but the overall red blood cell, the overall plasma volume tends to be lower. And that's fundamentally because what they do is you've only got X amount of blood volume that you can work with. They get a reduction in plasma volume to compensate for the expansion in the erythrocyte concentration. So it's not surprising that you would go from something like a 55% plasma volume concentration in an endurance athlete to something in the region that we saw in the previous data set of 48, even down to 45. The problem with that is fundamentally it then puts an increased stress on the cardiovascular system, and therefore we have to get the increase in things like blood pressure to facilitate that delivery of the oxygenated blood. If you have a high plasma volume, it can, though, in itself actually increase exercise capacity. Why? Because it increases cardiac output, and you therefore reduce blood viscosity. You've made the blood fundamentally thinner. So this is one of the things that's often looked at, particularly when you are working with clinical patients, is a simple way of reducing, in a very ill patient, a simple way of reducing cardiovascular strain is simply to pump in fluid. If you pump in fluid, this is a classic IV drip scenario, what you are fundamentally doing is expanding the plasma volume. Now, in that scenario, I am not reducing the erythrocyte count. I'm simply expanding the plasma volume. By expanding the plasma volume, you reduce the blood viscosity, and that therefore facilitates an increased cardiac output. You've got more blood per volume per beat of the heart. So the net result is that actually you would start to get a reduction in things like heart rate. And that's why using things like plasma volume expanders in a clinical population group is a very good way of improving oxygen delivery to the muscle. So when somebody's perhaps struggling, as we saw maybe during things like the COVID-19 pandemic, or as we see, in for example, COPD patients, a really simple way that can be adopted under clinical conditions just to increase oxygen delivery is increase plasma volume. It sounds counterintuitive, but it reduces the viscosity. It therefore makes the blood flow more effectively, reduces the blood pressure, but allows us to have a greater volume being ejected per beat of the heart. Here we can see it's quite old data from Sorka's group published in early 2000s. And what you've got here is you've got days of training. So it's actually fascinating. You've got about an 80-day training study. And what you can see is the changes in the three key variables. And these are delta scores, these percentage changes. So what you can see is changes in blood volume, which is you can see in the solid black dots, plasma volume and erythrocyte volume. And what you can see in the initial early stages is you get a very high spike in the erythrocyte volume. So the erythrocyte count goes up. But notice that over time, the erythrocyte, the plasma volume, apologies, I'll start again. The plasma volume concentration expands very, very rapidly in the first few days of training. While it's doing that, not surprisingly, there has to be an increase in the blood volume to compensate that. You're increasing just the total volume, as we were talking about a moment ago in our clinical population groups. But over time, that plasma volume starts to decline, and it starts to decline as we start to get an increase in the erythrocyte concentration. So you're looking here at around about 20 days before you start to see an increase in the erythrocyte volume. And so the net result is that both plasma volume declines and blood volume bounces back to where it was at baseline. But you're looking at here at around about a 10% increase over an 80-day period in the erythrocyte volume. There is initially about a 20% increase in plasma volume. That then declines back again to baseline. So you get this initial expansion, which is the fundamental compensation in terms of increasing cardiac output, increases stroke volume, allows for us fundamentally to probably get a reduction in heart rate, but fundamentally we get a reduction in blood pressure, allowing for that facilitation of the oxygenated blood to the muscle. Over time, as we create the hypoxic environment in the cell, the net result is we get the increase in the CO2 concentration, triggers the process of erythropoiesis, and we gradually get this increase over from the start of day 20, over about a 10-day period following that, we get about a 10% increase, as you see here, in the erythrocyte volume, red blood cell count. And here we take this data slightly further. What they've got here is plasma volume, erythrocyte volume, and VO2 max. And this is, you can see, kind of less than 11 days of training. So here you get that significant expansion in plasma volume, and you get a slight increase in the VO2 max over the first 11 days. Why? Well, you fundamentally don't get that because you've got an increase in erythrocyte volume. There's almost none. You're fundamentally getting that because you've got an increased cardiac output as a result of the increase in plasma volume. And if you want to know more about things like cardiac output, go and address the session which is on cardiovascular responses to exercise. Once we go to beyond 21 days, remember now plasma volume is starting to decrease, which you start to see. You start to get an increase in the erythrocyte volume. That increase in the erythrocyte volume is what drives up its proportional increase here in the VO2 max. Now, that's not to say there haven't been other biological changes. There almost certainly would have been. There would have been an increase in things like cardiac output. There would have been an increase in the morphological structure within the heart, both the eccentric and concentric hypertrophy of the myocardium. But fundamentally you can see there is an association, it is an association between the erythrocyte volume and the changes in the VO2 max. And if we go slightly further, this is just a summary of studies, and what they're looking at here is the changes in things like blood volume and plasma volume, and red cell volume. But let's just deal with blood volume overall and plasma volume. And these are kind of training based studies in both males and females. And what you can see is that you can see quite significant changes after 1 day here in plasma volume. But if we then go down to 112 days here, for example, actually it's almost no different, because as we saw in the previous graph from Sorka's group, the plasma volume starts to decline after around about 10 days. So actually when you end up here, it's not surprising, it's not much different to what Pugh's group is showing here. These initial surges that you're seeing here is that kind of initial plasma volume expansion with fluid retention to compensate for the extra stress that's being placed on the body during training, to allow for us to reduce the blood pressure, to increase the delivery of oxygen. As we get the biological adaptation over time in terms of the process of erythropoiesis, the plasma volume starts to decline, which is what you see as the duration of the training exposure increases, and eventually you would start to see them get very, very close back to baseline. The blood volume, on the other hand, if you look, barely changes over that period of time, because the blood volume is a function of both the plasma volume and the erythrocyte count. Now this is a really unique data set. So this is data that was taken from the CSC professional male road cycling team. And what they've got here is the blood data that they collect. They have to collect this as part of being a professional road cyclist. And what it shows you is each line represents a rider. So what you've got here is the average for the normal population of hemoglobin concentration of around about 14.2, 14.3 grams per deciliter. This is kind of the upper level for the UCI, and beyond this level, they consider it to be clinically dangerous, and actually they would withdraw the riders if the hemoglobin went above this point. But what you can see is in the majority of the riders, they spend the majority of the time above the average hemoglobin concentration. There are some variances. You've got this one rider here who never really gets above it, and in fact they have an enormous decline at this point. But the majority of riders are way above the average for the general population, because if you think about being an endurance athlete, one of the key attributes is being able to utilize oxygen. That's what it means to be an aerobically trained athlete. You go back to that schematic of the kind of the cogs that we showed earlier on, then the key variable that connects all of those is the ability to move oxygen in the circulation. You need the high hemoglobin concentration. But the other thing you'll notice, both in the hemoglobin and then if you look at this in the hematocrit, notice how variable this data is, both in terms of time points. So it clearly responds to what we're doing in terms of training and the environment that we are in, but also how variable it is across participants. Huge difference in terms of different athletes, despite the fact they're all doing very, very similar training interventions. And I mentioned previously about the exposure to altitude. So this is data where they've exposed people to what is called 26 days of living high and training low. So live high, train low means that you expose people to the altitude conditions, which is where they will live. So altitude is anything really which is in excess of about 1,500 meters above sea level. So anything above that, the barometric pressure starts to decrease. That's the weight of the column of air above you. So the difference between the pressure within the human body and the ambient air pressure starts to reduce. That therefore means the ability to get oxygen into the circulation is harder. And because the pressure gap's smaller, it makes it harder then to, one, get oxygen in from the atmospheric air into the respiratory system, but then also it makes it harder to then release the oxygen from the respiratory system into the circulation. So what you can see here is a 5,000 meter runner, a marathon runner. These are just kinds of case study data, but here you can see. So if you look at the hemoglobin mass rises after 26 days, erythrocyte volume significant increase, 6.3% increase. Plasma volume has expanded. Remember, it's 26 days. It's gone up. You would expect it probably to start to come down. But altitude is quite unique, because one of the things that happens at altitude is that it also changes our ability to retain fluid. Because we are changing the atmospheric pressure, we actually end up retaining more fluid, because the one thing that happens at altitude is you're putting greater strain on the cardiovascular system. You're increasing things like blood pressure. So one of the ways to compensate for that, which is different to being at sea level, is we retain fluid. Blood volume has increased as well. So actually what you see is the individuals will look slightly more puffy in the face when you look at individuals who are at altitude, despite the fact they'll be losing mass. And so the reason for that is you're retaining more fluid. So blood volume increases primarily because you've increased erythrocyte volume and you've increased plasma volume. And you can see here, this is the hemoglobin concentration. The actual hemoglobin concentration in this individual, and in fact the marathon runner, didn't really change. But what they did get was the increase in the erythrocyte volume. And this is one of the things that's perhaps misunderstood about altitude. People automatically think that altitude's really beneficial. Not for hemoglobin, it's not. You can see it in both cases here. You won't really start to see the effect in terms of the hemoglobin until they really come back to sea level. But you can get a sense here of the direct effect of reducing the partial pressure of oxygen, which therefore triggers a hypoxic state in the cell, which triggers the process of erythropoiesis, which triggers the increase in erythrocyte volume, which triggers an increase in hemoglobin mass rather than hemoglobin as grams per litre. Because remember, the plasma volume and the blood volume have expanded. So actually, when you look at this increase in the total hemoglobin, which has gone up, when I look at it proportionally to the increase in overall volume, it doesn't look like it's changed. So that's why that becomes the important variable over time.